Welcome back to Real Analysis. Today we're talking about continuous functions. We saw in class last time that there's some really strange functions out there in real analysis, particularly this Dirichlet function. And at the end of this lecture, I'm going to show you one that, in my opinion, is even stranger and kind of just shows us that even though we can use our thoughts about continuity to guide our proofs, we really have to use the definitions if we want to make any progress defining continuous things, because there are functions out there that kind of break our intuition and break what we expect. In this video, we're going to have two really big theorems, which are important and kind of give us a picture of one of the themes that will show up kind of at the end of this semester, the idea of mapping sets from one space to another space. But okay, first, continuous functions. What is a continuous function? Well, we'll start by saying f of x is continuous at a point. F of x is continuous at a if, and then what we're going to do is, well, the continuous definition is just like having the limit existing, because if you kind of think back to calculus, continuous functions are just functions whose limit always exists, but they don't have any holes or jumps or anything. So they're like our limit functions without the possibility of there being a problem at a. So I'm going to rewrite our limit definition. For all epsilon greater than 0, there exists a delta greater than 0, such that if x minus a is less than delta, then f of x minus f of a is less than epsilon. So this is basically our limit definition with two small changes. Our limit definition, we had a greater than 0 here. So for our limit definition for this part, we forced this inequality to always be bigger than 0. And this time we're not, and the reason is if it's continuous, we expect there to be no holes in our graph, so that inequality can equal 0 as much as we want. Second, for our limit definition, we always use just some L here, and now we're doing the actual value of the function, and that's because we're not saying that the limit converges to some random value. It's converging to the actual value of the function. That's because there are no holes or gaps or anything like that in our continuous function. So this is going to be our definition. Let's see, an alternate way of thinking about the definition is to say this. So an alternate definition is f is continuous at a if, we could just say if two things happen. One, the limit as x approaches a of f of x exists. And two, the limit as x approaches a of f of x equals f of a. Maybe I should say exists and f of a exists. And two, the limit of f of x equals the limit of f of a. And this is the definition you usually see like in your calculus textbook. One more note, and that is, so right now I'm talking about a limit at a point a. We say f of x is continuous on some set. Is continuous on a set E if it's continuous at every point on E. Maybe I'll take that arrow off. If it is continuous at every point in E. Okay, so that kind of makes sense, right? So it's continuous on a set. If every point in that set, it's continuous. But this just lets us, we talk about continuous in two different ways in mathematics. We talk about continuous at a single point, and that's where we've got our nice epsilon delta definitions. And then we have continuous on a set, and that means you pick any point in the set, and you can use this definition again. So continuous in both senses work. All right, so So now that we know what a continuous function is, it's so closely related to the idea of limits that all of our limit definitions are going to still exist. For example, f and g continuous. Well, this is going to tell us that f plus g is continuous. Okay, I'm going to be lazy writing this. F times g is continuous. F divided by g is continuous as long as g doesn't equal 0, right? G of a doesn't equal 0. So all of these kind of classical definitions exist. But there's one more that's actually going to be really important today, because this is going to kind of be the theorem that we leverage a couple times in a couple different places today. But it's that we know that we have the sequential definition of limits. Well, we have the same idea for a sequential definition of continuity, and that is f is continuous at a if and only if for every sequence, I'll say for every sequence xn approaching a, f of xn approaches f of f of xn approaches f of a. Sorry about that. I accidentally hit the little button on my iPad that went to the home screen. So you all got to see my beautiful background from Avila, Spain, which is where our family got to spend some time a couple years ago. Okay, at any rate, for every sequence xn approaches a, f of xn approaches f of a. So this is a really nice definition because it lets us talk about continuity in terms of talking about sequences. And we're going to leverage this definition a couple times today. I should probably be a little bit more careful in this definition. I'm kind of being a little bit lazy as we write this. We should probably talk about our function f, and that is our function f. You need to usually define what the domain is, and then kind of define things about the domain. So usually we'll say let f go from A to B or something, and then this point A has to be a point inside of A and B. Often we even let it be an interval. And then this sequence is in the interval, made up of points in that interval. So I'm being a little bit lazy, but you all can kind of look at the textbook and fill in all the pieces that go around this. But first, before we go tackling these big theorems, let's talk about one that's one more extension of the idea of like you can add continuous functions, multiply and divide, and still get continuous functions. And this is a theorem that we haven't had in the past, and it's talking about composition functions. And so this idea of composition functions, you'll remember back from algebra and calculus class, right? So G composed with F. This is just saying G of f of x. This is just putting the f of x function in the g of x function. And the reason why we've never been able to use this until now is because whenever we talked about limits, we could have had something very weird happening at that limit point. And so if we were to take another function that converged to that limit point, well, you've always got the possibility that that function does some strange things. Like, for example, that function could actually hit that limit point a lot of times. So, and that creates all sorts of issues for trying to compose the functions. Like for example, if your function f of x, was something like 1 if x is not equal to 0, and 0 if x equals 0, then that's a pretty simple function, and it just has a hole here at 0 with a dot, but the rest of the function is that. Okay, so therefore it's pretty clear that the limit as x approaches 0 is equal to 1 of our function, is equal to 1. But if we started trying to stick another function inside of that, well, you could potentially have a function that converges to 0, like the function x, like the function g of x is always equal to 0. And that would give you something very different, right? So g of x equal to 0 converges to 0, but if you plug it in, you're not going to get the limit equals to 1. And so you kind of get these inconsistencies, and all these consistencies happen right around, this point where the limit exists and where we let that point be deleted or moved. But now that we're talking about continuous functions, we don't have that issue anymore. So now we can talk about composition, and composition ends up being really useful. Okay, I hope some of that made sense. I feel like I'm rambling just a little bit. But let's prove this theorem and go for it. So first, let's look a little bit at our assumptions here. F goes from A to B, G goes from B to R, and f of x is in B for all x and A. So all that means is that whatever the domain of this G function is, all the f of x functions go into the domain. Otherwise, we would have points where g of f of x is not defined. So all these assumptions are doing is just kind of making sure that g of f of x is always always a defined function. Okay. So how do we do a proof like this? Well, the proof is actually quite simple. We're trying to make, we think of our last line. So our last line is going to look something like, our first line, is going to be let epsilon be greater than 0. And then our last line is going to look something like this. G of f of x, and I'm going to use this notation. G of f of, so G of f of x minus G of f of a is less than epsilon. So you can kind of see, already what's going to happen here. So epsilon's greater than 0. We're trying to get this expression because that's what it would mean for G composed with f to be continuous if we can find a delta such that this is always the case. Well, we can do this because we can just let f of x minus f of a be really close to each other because f is continuous, and then we can let x minus a be really close to each other by using our definitions. So really, we let x and a be really close. That forces f of x and f of a to be really close, and that forces g of f of x and minus g of f of a to be really close together. And so this is at the heart of our proof, but we kind of have to write these backwards to make it all make sense. So let's go through here and kind of make sense of all this. Okay, so since g of x is continuous, we can say that there exists some sort of delta greater than 0 such that if x minus, f of a is less than delta, then g of x minus g of f of a is less than epsilon. And here we're just using this fact that g is continuous at f of a. So we use that fact, and that fact tells us that we can find a delta where when x gets really close to f of a, g of f of x is minus g of f of a is less than epsilon. Okay, so let's now take that fact and move it to the next one. And now I'm going to find another delta that makes this statement true. And I can do this because I know f of x is continuous at a. So I know that since delta is a positive number, I can make x minus f of a less than delta. So I'm going to say there exists, and I need a new letter, so I'm not going to use delta again. I'm going to use a lowercase sigma. It kind of looks like delta. There's no reason why I would choose this and not some other letter, but okay. So there exists a sigma greater than 0 such that if x minus a is less than that sigma value, then f of x, let's come back just a moment, f of x minus f of a is less than epsilon, or is less than delta. Okay, so I've chosen kind of this second sigma value. Okay, so therefore I can now finally start putting it all together. So therefore I can start saying something like this. Therefore, g of f of x, okay, so therefore let's write this, if x minus a is less than, not delta, is less than sigma. So this is actually like the value that's our delta in our usual definition, because this is the smallest one. So if x minus a is less than delta, then what do we get? Then let's look at this inequality here at the bottom and see if we can force that to be true. Then the absolute value of g of f of x minus g of f of a, well, what is this going to be less than? Well, let's look really closely. So I'm gonna delete this for just a second and then come back. I probably shouldn't have written that out yet. If that's the case, then f of x minus f of a has to be less than delta by the previous theorem that we just wrote. But then what does that mean? Well, then if f of x minus delta f of a, notice up here I used an x, but this can really be any value that's closer than f of a. So now I have the premise of my green line up here. So then g of f of x minus g of f of a, minus g of f of a has to be less than epsilon. And that finishes our proof. So what you can see is that we started with this value less than sigma. That forced my f values to be less than delta, but my f values being less than delta forces my g of f values to be less than epsilon. Okay, hopefully that makes a little bit of sense. That's kind of at the heart of this proof. There are other ways. I could have proved it with sequences, by the way. So a sequence proof probably would have been a little bit simpler, and it would have just looked something like this. It would have just said let x of n approach a, then f of x of n approaches f of a by, let f of x of n approach f of a by the sequence definition, because we know if it's continuous and x n approaches x of a, then f of x n approach f of a. And then then we have another sequence. So then by the fact that g is continuous, g of f of x of n has to approach g of g of f of a. And so then for an arbitrary sequence, g of f of x of n has to approach g of f of a, and so that proves our theorem. That was probably the easier proof, but I wanted you all to see how we might work with some epsilons and deltas with this composition function to make it all make sense. All right, it's time to start talking about our big theorems. Big theorem number one is called the extreme value theorem. And let me just kind of give you a picture of this extreme value theorem and we'll think about it. This is something that shows up in Calc 1 a lot. And all the extreme value theorem really says is that if we have a closed interval, so we're going to start at A and start at B. Some people call this like the closed interval theorem or something. And think if we have a continuous function between A and B, what has to happen? Well, your function comes here. It can go up, it can come down, it can do all sorts of things, and then it stops at B. Oh, I guess the closed interval theorem is something a little bit more complex that we'll talk about. But all the extreme value theorem says is that somewhere in here there has to be a maximum and a minimum. So if I look, here's my minimum value and here's my maximum value. And so the extreme value theorem says there has to be maximum and minimums somewhere on this interval. And why is that? Well, if there wasn't a maximum or minimum, then that means you're doing something like this. Either you have some point where your function has an asymptote, like is going off to infinity or something, but that's not allowed because our function is not going to be continuous there. Or if that's not the case, then you have some situation where like your function is approaching some value but never actually reaches the value. But then that would mean you'd have to have an empty hole somewhere. So we can see that our intuitive idea of continuity tells us that we definitely have to hit the largest and smallest values somewhere within that region. And as I said, in calculus, this is super useful because once you know that it has to actually hit the maximum and minimum value, then we can use what's called the closed interval method Some people call it the candidates test, and that's where we go find all the critical values and check them and see which one's the biggest and which one's the smallest. And we're able to do this in calculus because we know that the max and min have to be somewhere in that interval, and they have to be one of these critical points. So once we check all the critical points, whichever one's the biggest has to be the largest. Okay, so that's at the heart of the extreme value theorem. But let's come look at the actual theorem itself and try to prove it. So there's actually two parts to the extreme value theorem. Let me come back. There's actually two parts to the extreme value theorem. So what we're going to try to show is that if I had this function that I was going, so if I have this function that's like this, that first the function has to be bounded, so that's an important element. And then second, I'll show that the min and the max have to be somehow contained within my interval I. So I is going to be this interval on the bottom. Okay, so let's do the first part first. Suppose I is a closed bounded interval and f from I to r is continuous. And these proofs, I'm just going to kind of leverage my sequence definitions both times. Before I go any further, though, we're going to use the Bolzano-Weierstrass theorem. And let's remember what the Bolzano-Weierstrass theorem said. So the Bolzano-Weierstrass theorem said that every bounded sequence has a convergent subsequence. Now, one important implication of this is that if it's bounded, if our sequence, and we didn't actually talk about this, but we should right now, that if it's a bounded sequence, say every xn is the sequence is between some little m. So every xn in the sequence is between some minimum value and some maximum value. Well, then what's important is that convergent subsequence converges to something, but what it converges to is also between the same minimum and maximum value. And that kind of makes sense. We could go and try to prove this, but it's really just a characterization of the comparison theorem. It doesn't make sense that your sequence could always be within m and m, and then your convergent sequence could somehow be outside of that value. Usually we'll put some equal signs here, but this is going to be useful. So what we're going to be doing is we're going to be using the sequence definition of continuity, showing that our sequence must be bounded. And then once we show that our sequence is bounded, finding a convergent subsequence, and that convergent subsequence is going to kind of do our work for us. Now, what that means is, as we do continuity, we're not going to actually have the continuous definition showing up a lot. We're not going to have the epsilons and deltas showing up or limits showing up, but they're all hidden in the fact that these sequences have to converge to the value of the function. So if it's not continuous, then when xn approaches a, f of xn doesn't have to approach f of a. In fact, f of a doesn't have to even exist. F of a could be anything else, right? But if it's continuous, then that forces f of xn to approach to f of a. And that's going to be what we're really going to leverage as we go through this theorem. Okay, so let's try to prove this first one. And I'm going to draw a picture over here. And again, like most proofs, I'm not going to go through all the gory details. We got the book for you to go through that, and you can enjoy that. But the big idea is this. We have our sequence, and it goes from some value. Let's see, I want to use a and b, but the book always uses a and for the value that the limit is approaching. So let's just use let's just let our interval I be here we can use Greek letters. We'll go from alpha to beta. So this will be our alpha, and this will be our beta. Okay, and so the question is, can our function at some point in here, if it's continuous, can we have the function at some point like grow so big that we can't see it and then come down? So can we be infinitely large? Well, okay, so here's the idea. The idea is that we're going to create a sequence of values within the interval alpha to beta. So we're going to create a sequence in the following way. create a sequence xn as xn by the following. For each n in the natural numbers, there exists some value in between a and b. There exists an xn such that f of xn is greater than n. Oh, I guess I should have done my premise. So I'm going to assume that f is not bounded. So by contradiction, we're going to do contradiction. Assume f is not bounded. And so what does it mean to be not bounded? Well, to be not bounded means that if you choose any value here, then there's always points that are bigger than that value. So like if this is n, then we're just going to go find some point here, xn, such that f of xn is bigger than that n. And if it's unbounded, I can do this for every xn. So x1 is a value that's bigger than 1. x2 is a value that f of x2 is bigger than 2. x3 is the value such that f of x3 is bigger than 3. Okay, so we're just consistently moving this n value upwards, and as the n value moves upwards, we're finding larger and larger values of the sequence. And so that's going to be our sequence xn. Okay, well, what we know is that all of these xn values are located somewhere. So these values, they could be kind of bouncing back and forth. All these xn values are located somewhere in between a and b. So our xn values, so what we know is that xn, the x values, not the f of x values, xn is bounded. Well, because the xn's are bounded, then that means it has to be there has to be a convergent subsequence. A convergent subsequence, xn with a little k, and that convergent subsequence converges to some number a in my interval alpha beta. So it converges to some a in here somewhere. So there's some subsequence of these things that converge to some value a. Okay, so there's some subsequence converging to a. So now we just ask ourselves the question, what is f of a? And we'll notice two things about f of a. Well, one, f of a has to be a real number because we have a function going from I to the real numbers, because f is a function from I to r. So one, f of a has to be a real number. But on the flip side, but for all n in the natural numbers, f of a is going to have to be bigger than n. And I can prove this because well, our f of xn's are approaching a. So this is where I might try to use some epsilons and deltas if I wanted to be really particular about it. And that is, I can always, if I have, say, x of 100, I can make a window. I can make a delta window around x of 100 such that the values are always bigger than 100, right? And so because it's continuous, and so a is within that window. So the point is that my f of a has to be bigger than every possible n, but this is actually not possible for a real valued function, right? So there are no real numbers bigger than every possible integer. Okay, so that kind of gets at the heart of how we're going to prove this thing. I didn't go through all the details. Again, consult the book to look at all the different details, but this is at the heart of it. We create some sequence that has to become infinitely large, but then that sequence has a subsequence that converges. But that convergent value has to both be infinitely large and not infinitely large at the same time, and that's a contradiction. So f must be bounded. If I have a closed and bounded interval and my function is continuous, then the resulting interval has to be bounded. So in other words, whenever I take my function and I start from alpha and from beta, then I'm not exactly sure what the values in the middle are here, but it has to be bounded. I have to be able to create some sort of smaller and larger value such that all of my function values are within that window. And we're actually going to use this when we prove the second half of the theorem. And that is, suppose it's closed and bounded, then there actually exists a point such that f of xm is equal to the sup. So because f of x is bounded, it has a sup value. So let's think about this picture here, just like I did a second ago. So if I've got my alpha and my beta here, then what we have is we have all of, we have all the function values kind of going around in here. And so we've got up here a sup, which is capital M, and we've got here an inf, which I'll call little m. And so our sequence must be bounded by these things. And so the question is there ever a value that actually hits this sup value, or is there not? Could our function become, one of these pictures where the function is getting closer and closer to the sup value, but not actually touching it? And so this is that second question. The reason why it's not is logically is that we don't have any holes or anything in here. But what we need to think about instead is just what's going on around this value. Well, the way we're going to do this is the exact same way we approached the last problem, and that is we're going to approach it by using a sequence. Okay, so we're going to take some sort of sequence that's getting close to the sup value, and then ask what does the limit of that sequence have to be. Well, what we know is that if there's a sup, then we're always able to find a value within epsilon of that sup. So we're going to create a sequence just like we did last time. Create xn such that our sup value, which is m minus 1 over n, is less than xn is less than or equal to capital M. Okay, and we could do this, if you remember, this is one of the properties of sups, that if I subtract just a little bit, you can always find an x value in it. Oh, sorry, not x of it. This is this is not xn. This is f of xn. Right. So because by the way, I should probably write what is my so where my sup is my inf of where my capital M is my sup of all of my f values. So every possible output value, I took the sup of all of them. Okay, so what we know is this sequence, whatever it is a sequence of values between a and b. So all of our x of n's are in the set, I say at a and b, alpha and beta. So that means the x of n's are bounded. And that means that it has a convergent subsequence by Bolzano-Weierstrass. So let x in k approach to a is a convergent subsequence. And again, I'm being a little bit lazy. And that was not a very good sequence, only has one q. Okay, I'm being a little bit lazy with my writing. It's because I've kind of got limited space. I don't want to kill you all with notation and details. I'd much rather you all take the time to go kind of look at the textbook and see how you spell the details out once you kind of understand the heart of what's going on in the proof. Okay, so what we've got is we've got a convergent subsequence, and so the question again, just like we did last time, is what about f of a? Well, let's notice something. So, okay, so the question now we ask again is, what about f of a? And one thing I'll notice is that m minus f of a, well, you'll see that m minus f of a must be less than 1 over n for all natural numbers n. And you could see this kind of, we would probably use like an epsilon delta argument again. And so that is, we would say, okay, if we've got this subsequence that's converging to a, and then the question is, well, what is f of a? Well, the answer is f of a can't be outside of 1 over n. So if I have like a 1 over n distance here, and then if I drop 1 over n down, a can't be outside of that, because then I could take a window and all my values would be outside of that 1 over n window, and that would mean that my sequence is not converging to f of a. My sequence is not converging to f of a anymore. So I can see that because each of my sequence values are getting closer, is within 1 over n of m, that my f of a itself has to be within 1 over n of m for all n. But what does this mean? Well, this is like a chapter 1 idea. If you have two values that are smaller than every positive number, oh, and I guess I could do the absolute value here, because then the only option is that they're actually equal, is that it actually equals 0. Then m minus f of a has to be 0 because it's smaller than every positive value. But then that just means that f of a is equal to our m value. Okay, again, a little bit sloppy, but this is at the heart of the proof, and you all can kind of see how this proof goes about it. The book did something a little bit different that I thought was cute, but I didn't like it quite as much as this structure. So this was a proof that I kind of came from looking at some other sources and thinking about the proof itself. So have fun. You can work out the details here, and this would be a really good one to do. Okay, so this was the first of our two big theorems. So what is this theorem telling us? It is just telling us that if we have a function, right, it says that if we have a continuous function, then what that means is that it has to have a max value somewhere in the interval, and it has to have a minimum value somewhere in the interval. And so the question now is, well, what about all the other points in the interval? Are we allowed to skip some points? So we have to hit a max somewhere. We have to hit a min somewhere. Could we skip a point? Is it possible that our function, right? Is it possible that our function actually we have some value in the middle where our function kind of goes and then it like jumps over it and never actually hits it, right? So is that something that can happen? And we kind of know intuitively that this feels bad, but we also know from looking at some of the functions the other day that some weird things can happen when you talk about continuity and not continuous and not continuous functions. So let's tackle this problem and see, and this is a theorem that we also do in Calculus 1 called, this is a theorem we also do in Calculus 1 called the intermediate value theorem. And so the intermediate value theorem just says exactly what we were talking about, and that is that if you have a function and f of a is right here, and f of b, if a is right here and b is right here, so this will be f of a and this will be f of b. So if that's continuous and I pick any number that lies in between them, so if I pick any y naught in between them, that this function must at some point cross that line y naught. And so there must be some x naught in this picture that eventually crosses that y naught line. Okay, so this is the intermediate value theorem. We do this in Calc 1. The Calc 1 students, I think, don't ever appreciate it. They kind of, and the reason is the theorem doesn't tell you how to find x naught. It just tells you there is an x naught. And so that's kind of a little bit off-putting for a calculus student. But mathematicians are often much less concerned with finding an answer than knowing it exists, because if we know an answer exists, you can use computers or something to estimate it or find your answer pretty quickly. But the question is usually, is there an answer? And that's usually the more interesting part of the math of calculus. Okay, so we're going to do something similar. I'm going to think about some sequences and some soups again. This time I'm not going to use a sequence, but I am going to kind of think a little bit about a set and some soups. So what I'm going to do for this proof is I'm going to take all of the points I'm going to collect all of the points such that f of x is less than this y naught. So if you see here, these are my points that f of x are y naught, and I'm going to collect all of those points and call them a set, and I will call them the set E. And then what we're going to do is we're going to talk about the sup of that set, and our claim is that the sup of that set is actually the point that has to hit y naught. And so what we're going to prove is that if that sup of the set is not the point that hits y naught, then we actually could have moved our set over, and the sup would have been a little bit bigger. So this is at the heart of our proof. So let's come and try to make sense of this using kind of proof type questions. So first thing I'm going to do is I'm going to let E be the set of all x in A to B, such that f of x is less than this y naught value. So notice E is a set in the domain. So E is not a set in the range, it's a set in the domain. And then, well, this set is obviously bounded above, and because it's bounded above, it has a sup. So I will let x naught equal the sup of E. Now I'm just going to ask myself a simple question, and I'm going to ask myself, is it possible for f of x naught to be less than y naught? So could f of x be less than y naught? Well, by contradiction, let's assume that the answer is yes. So let's go ahead and change colors here while we're at it. So by contradiction, we will assume that f of x naught is actually less than y naught. Well, then what we can do is, if f of x is less than y naught, so let me come over here and draw a little bit for us. So let's erase some of this and see what's going on. So what if I've got my set, and my set looks something like this? So let's draw that picture again, and we'll have A and B and f of A and f of B and then y naught. Okay, so let's take my picture and ask, well, what if I've got what if my function kind of comes up here, but then doesn't actually hit B, and we've got it. I know this looks like a jump, but what if it does something mysterious in this area, and it doesn't actually go across that? So that would make our set E look like this. So that would be our set E. Okay. So the question is, what if this x naught value, which is right here, is actually smaller than y naught? Not equal to y naught, but smaller than y naught. Well, what we're going to do is we're going to show that if that's the case, because it's continuous, then there have to be some other values on the other side of y naught that are also smaller, on the other side of x naught that are also smaller, and so we can move that sup over to the right. So that's kind of at the heart of what this proof is going to say. Okay, so what I'm going to do now is I'm going to let epsilon be this value right around, I will let epsilon be kind of this value right around the y naught, and then I'm going to find a delta value that here around the x naught that all has to go within that epsilon range. And what that means is now, once I've done this, I'm going to have some values which are over here, which are bigger than x naught, but still smaller than y naught. So this is kind of at the heart of what I'm going to write for my proof. Hopefully that makes a little bit of sense. Okay, so let f of x naught be less than y naught. Then we're going to let epsilon equal y naught minus f of x naught. Then that's just this, right? That's just this distance between y naught and f of x naught. Then there exists a delta such that if x minus x naught is less than delta, we know that that f of x minus f of x naught is less than epsilon. But what does that mean? Well, that just means that f of x is less than f of x naught plus epsilon. So all I've done is I've now broken this up by, by saying f of x minus f of x naught is between negative epsilon and positive epsilon, and then I added the f of x naught to the other side. So f of x is less than that. I could do the other side of this inequality, but we don't care about that side. Is not the important side. This is the important side. But this is now equal to f of x naught plus y naught minus f of x naught, because that's what we defined epsilon to be. And so that means this thing equals y naught. All right, so what we've done is we know that f of x has to be less than y naught. So that means I'm going to have to erase myself some stuff here so that I have some more room to write. So what this means is that for every x in this region, for every x in this delta region, the f of x is in this epsilon region. But that means we can just let x be bigger than f of x naught. So we can just let x be some number bigger than x naught, such that x minus x naught is less than delta. But then what we see is that means that f of that x value is less. Let's call it x1. But that means f of that x1 value is still less than y naught. Okay, but that means that this x1 is in our set E, and x1 is bigger than x naught. But that would tell us that x naught is not the sup of E, right? Because we just found an element in E bigger than what we said was the sup, but that is not what sup means. Sup means it's larger than every value in E. Okay, again, a little bit sloppy, and again, the book gets a little bit cute in trying to prove this, but I think this is at the heart of the proof. And if you look kind of through the lines, in between lines of the book's proof, you'll see they're trying to do something just like this. They used a lemma to prove this theorem, kind of a more general lemma, and then instead of thinking about this, they subtracted everything down so that we're talking about 0 instead of talking about 1. But what does the lemma say? The lemma just says that if you have a value bigger than 0, you can find a value larger than it, which is still bigger than 0, and all of that. Okay, so let me just talk just a little bit about what this tells us. So this gives us kind of a really important picture of continuous functions. And I've drawn this a bunch of times, but that means if we have A and B, if it's continuous, we have two things happening. We have that our function hits its maximum values, m, and it also, maybe we'll make this our minimum value. But also, if we take any point, and notice we really just said points between the beginning A and B, but we could take any point between any value. So we have little m and little m, and also if we take any point within little m, that point is also that point is also hit by the function. So what this means is that if I think of this as mapping a function, f of the closed interval AB, well, my output also has to be a closed interval, m to capital M. And so that means continuous functions map intervals to intervals. Notice this is not true for not continuous functions, right? So if your function is not continuous, then you don't have to map it to an interval. You can map it, for example, if you use that Dirichlet function, then the Dirichlet function, remember that's the function that sends all the rational numbers to the number 1 and sends all the irrational numbers to the number 0. The Dirichlet function, if we look at f of 0 and 1, it is just 2 points, just the point 0 and 1. And that is definitely not an interval. It's just 2 points. There's nothing in between, right? Similarly, if you look at something like 1 over x, 1 over x would send the set 0, 1 to the set, like 1 to infinity, right? So functions that aren't continuous don't have this property, and not only that, sets that aren't intervals don't have this property. So 1 over x is continuous for the closed interval 0 to 1. But for that, I mean, let's do like the partially closed interval 0 to 1, but that maps to the interval 1 to infinity, which has very different properties than the original property. But furthermore, I could come up with a function that maps, say, the set 0, 1 to the closed set 0, 1. And so it turns out that there are two important questions. The important question is, what type of sets satisfy this mapping? And it turns out that there's a more generalized idea of what it means to be an interval. We'll say those sets are closed and bounded, and then we'll go even further than that at the very end of the semester and say these sets are compact. And so compact sets always get mapped to compact sets. And then there's also a similar idea, which is the backwards question, and we'll talk about that again. So this is kind of a preview of the future of the class. Maybe the last week of the class, we'll talk a little bit about mapping with these functions. What if we put a set into a function, what does the set coming out of the function have to look like? It turns out if the function is continuous, then we know a lot of things. We can make a lot of nice predictions about what the set coming out is going to look like. If it's not continuous, then we can't. Okay, let's come to this monster, a truly mesmerizing function. So here's our function. F of x is going to be the set, and I'm going to call it the set 1 over q if x is equal to a rational number p over q in reduced form. Okay, so notice we have to say it's reduced, otherwise this isn't well defined, because then 0.5 could be 1/2 or 2/4 or 3/8 or 4/8 or something, and so this q has lots of values. So we use the reduced one, so 0.5 goes to the number 1/2. And it's going to be 0 if x is not a rational number. Okay, so this is actually a really interesting function. Let's just quickly think about what are some examples. So, for example, f of 3/4 is 1/4. F of 22/7 is 1/7. F of pi is 0, right? So if it's rational, then it goes to 1 over whatever that denominator was. It like only keeps the denominator and throws out the numerator. And if it's irrational, it goes to 0. So let's ask an interesting question about kind of some of these functions. So what happens nearby some of these functions? Well, let's notice what happens nearby a rational function or near an irrational function. So if x is not a rational number, then we'll notice something that's the so if x is if x is a rational number, then we notice that f of x is definitely going to be bigger than 0, assuming that x is not 0. X is a rational number other than 0. Then you'll notice that f of x is positive because it's some number. So f of x is equal to p over q. P over q, not p over q, is equal to 1 over q, which is strictly greater than 0. And so if I think of this on a function, then if I have my x value here, then 1 over q is its value. But what you'll notice is that any sort of window around this, any sort of delta window that I want to make, always contains irrational numbers. There are always irrational numbers inside of these. And so because of that, any delta window always has zeros, values that are 0 in it. So that means that f of x can't be continuous at the rational numbers. So because of that, 1 over q is greater than 0, and so for all delta greater than 0, there exists, let's just say some y. How about let's do z, some sort of z in the set x minus delta, x plus delta, such that z is not rational. And so then that obviously tells us that f is not continuous. Is not continuous at a rational number. So every rational number, the set is not continuous, right? Okay, so that makes sense. Now, what about the irrational numbers, however? Well, the irrational numbers, it behaves quite a bit different. So first, hopefully it's clear that if it's rational, then the set is obviously not continuous, because your function's up here, and there are always zero functions nearby, forcing it to be not continuous at that point. But what if x is irrational? So if x is not a rational number, then that value, then f of x is equal to 0. So that value is right here on the dot. Well, here's the question. If I pick any sort of epsilon, can I find a set of values, say, can I find a delta, such that every value within that range is less than delta? And it turns out that the answer is yes. Okay, so how would I convince myself of this? Instead of epsilon, let's just pick, like, say, a 1 over n that's even smaller than epsilon. Well, then all I have to do is I just have to make delta small enough that no 1 over n could possibly fit in this range. So I make it where the 1 over n's are all outside of my range. So for example, if this is 1/10, then all I have to do is I just have to, like, take the minimum, or the inf, of x minus, x minus k over 10 for all k in the natural numbers. Okay, so these can never be 0. If it was 0, then that would mean that x is rational. And so I just take, well, what's the smallest distance between x and the nearest value that's divided by a tenth, that's divided by 10, and, well, okay, just let delta be less than whatever that value is. Then just let delta be whatever that inf value is. So in other words, if I draw my picture here, I'm doing, say I've got 1/10, I'll put 1/10, 2/10, 3/10, 4/10, 5, 6, 7, 8, 9, 10, 11, 12, 13. Actually, I probably shouldn't use just 10, because I don't want a number bigger than 10 either. So let's come here and make some slight adjustments to the set. Sorry, I'm kind of doing this on the fly. X over n, such that k is a natural number, and n equals not 1. I guess 1 is fine. 1 to up to whatever my n. Let's make this a capital N value. And we'll make this like a capital N value. So in this case, it would be 10. Tell you what, we'll just go 1, 2, and we'll use 10 as our capital N value. Okay, so what that means? That means I put a bunch of dots for all of my 10s. I'm then going to go put some more dots for all of my 9s. Put some more dots for all of my 8s, and just keep doing this. And it turns out that one of those dots, I don't know which one of those dots is the closest. And so this is the closest of all the fractions that have, they're divided by 1, divided by 2, divided by 3, divided by 4, up to 10. So that's the closest of all of these fractions where 1 over q, that's the closest fraction where 1 over q, where q is, say, greater than, where q is less than or equal to 10. Okay, sorry, I'm doing crazy things with my colors here. Well, what that means is if I make my little window, less than that inf, then that means that all of my values of my function are smaller than that 1/10. So all of my values of my function are within that range. But then I could do the same thing for 100. I could just make my window even smaller. So if delta is less than the inf, then for all x minus, let's call our point x naught. all x minus x naught less than delta, f of x minus 0, which is just f of x, is going to be less than that epsilon value. All right, so what does this mean? Well, what this means is that this function is actually continuous at this point, because I can always make a window close enough to x naught that all my values are within epsilon of that window. And this is, why does this happen? Well, it's just because fractions, as you make fractions more and more precise, the denominator of that fraction gets larger and larger and larger. So if I was trying to approximate, say pi, I might approximate pi with a fraction that looks like this. So we know that pi is 3.14159 dot dot yada. So I might first, well, let's just approximate it by the number 3 over 1. Well, so then now that gets mapped to the number 1 on my picture. Well, next, I might approximate it by 31 over 10. That goes to 1/10. And that's a little bit closer than my 1 was. Next, I might approximate it by 314 over 100. And notice that's going to get mapped to 1/100th, which is really closer. And it turns out that the closer I approximate this thing, I'm always forced to use larger and larger denominators to get better and better and better approximations. Okay, so what's the final conclusion to this lovely, crazy function? Well, this lovely, crazy function has two interesting properties. One, this function is continuous at every irrational number. But it is simultaneously not continuous at every rational number. So this means that somehow when you look at the number line, well, we know that if you take any window, they're both rational and irrational numbers. So no matter how far you zoom in, you will always have points where this function is both continuous and non-continuous, and they're just living right there interlaced with each other. So people have tried to make graphs of this. So here's kind of a graph that you can find on Wikipedia that looks like it. So you can kind of see what these function values look like. And so what you notice is that if you pick any rational number, it's obviously discontinuous at that rational number because there aren't points near it. But if you pick a 0 value, all the values nearby, if you get close enough, it ends up becoming 0 because this value isn't actually underneath that dot, it's just slightly adjacent to that dot. So if you keep zooming your window in, it's like if I take, say this dot right here, I could start with a big window that has high points like that, but I can eventually make my window smaller enough that that high point isn't included, and now this is my highest point. So I'll take my window even smaller, that now my highest point is that one. And I keep doing that, and then I can eventually make my window as small as I possibly want. So this is a crazy function, and I think, I don't know, I find it mesmerizing, and I really enjoy it. Okay. Because the videos are coming a little bit late, I want to spend a little bit of time today instead of me giving you a new task to do. I want you to go back and look through your notes, look through your homework, and write down several problems that we've done up to now that are still kind of nagging you or still challenging you. And I might try to devote a little bit of time at the beginning of class, and we can work some of these problems together and talk about them. So go back through your notes, find these nagging, challenging problems from the first week and a half of class, write them down, and come to class with those. I do have one more video. It's going to come out probably in the next couple hours, but I'll try to have that for you before class. It'll be shorter. All right,